Oh, hey man. Yo, check this out. I just bought this physical Bitcoin wallet.
Physical? Wait, why don't you encrypt it onto your computer?
Well, I feel like these days, so many hackers out there, they break everything. I don't think it's safe.
Well, let's hope they don't break into this one. Hey, why the long face?
Well, I just lost a lot of my Bitcoins.
Oh, that's so sad.
Yeah, they're all in this wallet. I don't know what could happen to them.
Wait, were you sure that your Bitcoin wallet was totally safe? That there weren't any Trojans in them?
Trojans?
Yeah.
In a physical wallet? Is that even possible?
Hi, I'm Santosh.
And I'm Darren.
And we are
IFT for Trojan Detection.
IFT for Trojan Detection is all about finding Trojans in hardware that leak our secret information.
Given an RTL netlist and some inputs, our goal is to determine if there are any gates that act like Trojans, and if so, to print them out. Take this integrated circuit as an example. Inside, it contains logic to encrypt a given message, based on a secret key that is also input. However, sometime between the design phase and the actual distribution of this chip, an extra component was inserted. The extra mux here provides another path for the secret key to follow, and under certain circumstances, the secret key will flow directly to the output, which can be seen by anyone. In this system, the mux is identified as a Trojan. Trojans can be very difficult to detect, as they can be very subtle changes that lie hiding within the design.
How do we know that information flows? Information flows from an input to an output if a change in that input results in a change in the output. Here, a change in input D from 0 to 1 results in a change in output O. So we say that information flows from input D to O. Traditionally, this solution is obtained by solving the Boolean satisfiability problem, which is very time-consuming. We, however, use this principle and take it to the gate level. Now, in this figure, if we can show that information through some modeling show that information from D flows to OP1 and from OP1 to O, then we can conclude that information flows from D to O. This granularity is achieved by modeling each gate in the gate level netlist to show information flow. This modeling is called shadow logic modeling. We have used two types of models in our design to determine Trojans. They are the conservative model and the precise model.
In this example, A and B are the inputs and O is the output. AT and BT indicate whether or not we want to track the inputs A or B. The conservative model states that if we are tracking an input to the gate, the information flows from that input to the output regardless of the actual inputs. In this example, because we are tracking the input A, the output will also be tracked, regardless of the actual values of A and B. With the precise model, we take into account the actual values of the inputs. The precise model states that the information flows from an input to the output if a change in the input being tracked results in a change in the output. If we change the input A to 0 and change it back to 1, the output does not change. Thus, there is no information flow to the output, and the output will not be tracked.
Now that we've covered the basics, let's see how we find our Trojans. On the left is a netlist. We also have an input file which has the values of all the inputs and the input that we want to track. Using the netlist and the input file, we build and populate our netlist graph. So the graph has been built and populated. Next, we set the model to be conservative and build a vector of list of signals on the path through which the information flows. We have the vector of paths. Then we set the model to be precise, and using a list of random input values, we build a frequency map which has many paths through which information flows and the number of times that path occurs. Finally, we use the results of the conservative model and the precise model to determine the paths on which our Trojans lie and finally the Trojans themselves. Thank you.